Welcome to the next video in the group theory series. Here you can see an overview of everything that we'll be talking about in this video. In this video, we follow up on the previous video by discussing how to compute products, i.e. compositions, of permutations when they're written in cycle form. In the page to the left, I've shown the process for the cycle 1, 2, 3 product 2, 4. For some variety here in handwriting, I'll show 1, 2, 3 product 2, 3. So I pick an element arbitrarily, let's say 1. We chase it. That means feeding it into the rightmost cycle. That cycle leaves it fixed, so we're next feeding 1 into the cycle 1, 2, 3. This sends 1 to 2, so we get a 2. And so we can see that 1 goes to 2. I guess mysteriously I wrote that as 2, 1. Not sure why. But in any case, it is correct that 1 does go to 2, so I'll leave it. Next, we chase 2, and so we feed 2 into the product. It sends to the rightmost permutation, sends 2 to 3. So now we're sending 3 into 1, 2, 3. This sends 3 to 1, so ultimately 2 goes to 1. So we have that part of the cycle. We haven't encountered everything yet, so we could chase 3. And we see that in the rightmost cycle, 3 goes to 2. So now we're sending 2 into 1, 2, 3. That sends 2 to 3. So ultimately, 3 goes to 3. And we could write this, so to speak, 1 cycle. It's just as well if we drop that off because in both cases, we see that 3 is left alone. It's fixed. So here you can see somewhat explicitly that 3 goes directly to 3, or here you can see that because it's not written, nothing happens to 3, and so also 3 goes to 3. Note that to be thorough, we need to specify from the outset that the set we are permuting is the set 1, 2, 3, or 1, 2, 3, 4, or whatever it may be. If the set of permutations is, say, S5, then we cannot stop at 3 as we did above. We would have to make sure that we know how our permutation maps 4 and 5. However, since 1, 2, 3 product 2, 3 doesn't contain 4, we can see in advance that even if this is taken in S5, it will leave 4 fixed. Likewise for 5. The upshot being that although it is technically required that we chase those elements, we can see that they will do nothing, and therefore we don't really have to write them, even in those situations. Whenever a permutation leaves an element fixed, we can write it. In the example above, we found the result 1, 2, 3, product 3, where 3 goes to 3. But we can also drop it since 2, 1 also leaves 3 fixed. Also, by the way, I've been writing permutations with commas. Often mathematicians omit the commas, but still use spaces. So for instance, instead of 1, 2, 3 with commas, it is common to write 1 space 2 space 3. Now we can't always drop writing fixed elements since that would lead us to write nothing for the identity permutation. In this special case, we usually write paren 1. As a final note, what are we actually getting when we compute the product of permutations? what we get is the representation as a product of disjoint permutations, or really disjoint cycles. So you can see in this other example that 1, 2, 3 product 1, 2, 4 results in 1, 3 product 2, 4. We call a permutation an M cycle if for some positive integer M, it is a sequence of elements, A1 through AM, in a single pair of parentheses for some elements in the set being permuted. So for instance, 3791 is a 4 cycle. We call a permutation a cycle if there is some positive integer M such that it is an M cycle. And we call cycles sigma and tau disjoint if, in cycle representation, they share no elements. So for instance, the cycle 135 and the cycle 27 are disjoint. So the calculation results in a product of disjoint cycles. As such, it makes it easy to read off what the permutation does to any given argument. There are other benefits to disjointness that we'll encounter later, such as commuting and related perks.